After these two examples of applications of Laplace method, we now can ask an important question. As you may have noticed, our derivation were devoted just to first non-trivial term of probably more complicated asymptotic series. And in principle, it could be interesting to figure out what are corrections to this first term. And this is the procedure to derive these corrections will be topic of this lecture. So again, recall the form of our general Laplace integral. And the form of the integrand of this expression tells us almost immediately what could be the good way to derive approximations to our procedure. And to be more precise, let us assume some specific situation. Suppose that function lambda f of x in the exponent has a single maxima in the integration domain. In fact, this is not a very restrictive assumption, and if there are several maxima of this function, then each of them should be treated separately. But for simplicity, we'll assume that this maximum is a single one. So, and suppose this maximal is attained at point x naught. And of course, the fact that this maximum exists there, and the assumption that the behavior in the vicinity of this maximum is quadratic, there is a very natural change of the integration variable. And in the assumptions which I just discussed, we may write that the following formula. And as soon as this approximation is legitimate one, we can switch our integration variable from x to t. And of course, in order to do this, we need to write it a bit more formally. And more formal procedure of what just described in words corresponds to the following. So, but we of course, this equation by itself defines function x of t, x of tau, implicitly. But assume that this implicit function is known for a second, and then the integrand in our formula for I of lambda takes the following form. The first two factors in this form are trivial. They just come from substitution of f of x of this form to our original formula. Of course, what is a bit less trivial is the change of the integration measure. And in order to make this integration measure explicit, we need to know what is the exact solution for this implicit equation. But suppose we can do this. We will see how this can be done in some particular example in the next lecture. But for a second, let's assume this is a problem which is solved. And then this function, treated as a function of x, can be, or as a function of tau, alternatively, can be expanded in a Taylor series in the vicinity of tau equal to 0. So recall that this tau equal to 0 corresponds to maximum of the expression in the exponent. So as soon as this Taylor series can be computed explicitly, the next step is almost trivial. And in fact, we are coming to almost a final result, and it takes a form of infinite sum. So the sum in this expression corresponds to different terms of the Taylor expansion, and each of the particular integrals here is our favorite Gaussian integral. To be more precise, let us discuss how to calculate this integral explicitly, each of these integrals. And according to the trick which was discussed in the first lecture, this integral can be calculated by differentiation over parameter. This works as follows. So first of all, notice that this integral under the differentiation sign is simple, and in fact this is a well known to you by now Gaussian integral. Let me write it explicitly. It is nothing but inverse square root of lambda, and from now on, from here we can go in two different ways. So first of all, it is clear that each differentiation over lambda puts down one t² factor in the integral sign. This way, we can figure out that this expression is equivalent to the left-hand side. But from the other side, as long as we know this exact value of this integral, we can just calculate the derivative explicitly. And this is how we come to the right-hand side of our expression. And as a result, doing calculation this way, we come to the explicit expression for each of the integrals which come to our final result. And this derivative can be calculated. And this calculation is quite straightforward. We just apply the chain rule to this derivative. And as a result, we have the following finite product. And each of the terms in this product comes from subsequent differentiation of the inverse square root of lambda. We can actually rewrite this expression as a bit more closed form, which is almost a trivial arithmetic exercise. And this closed form is as follows. It's just combined of different factorials, which all have combinatorial nature and come as a result of application of the chain rule to the derivative. And finally, our next step is to use this explicit expression for each of the integrals and substitute it to our infinite sum. As a result, expression for the contribution to the asymptotic series which comes from the vicinity of the extremal point x0 is the following. For now on, this discussion can seem a bit abstract, but in the next lecture you will see how to apply this procedure to calculation of some particular asymptotic of an integral. Let us now turn to some particular example of how these generalities about a full asymptotic series from Laplace method can be applied. So we will evaluate the first two terms of an asymptotic expansion of the following integral. In fact, this integral is closely connected to Bessel functions, but we will not use this for now, and instead we will apply what we have just learned to calculate its asymptotics. As you already see from this expression, the exponent doesn't have our standard form, but we already know how to deal with it. So first of all, let us see how do we change the integration variable in order to reduce our integral to our well-known Gaussian integrals. So this logic stays behind the whole method of building asymptotics by Laplace method. And of course, as we have just seen, we need to understand how to reduce the expression in the exponential to simple quadratic function of new integration variable tau. And in this case, this can be achieved by the following implicit definition for tau of t. So suppose we take this formula as an implicit way to define new integration variable tau. You will see in a second how this helps us, but let us first concentrate on this equation and try to solve it to some accuracy. Of course, this equation as it is written cannot be solved exactly, but as we anticipate, integration variable tau which enters this formula will be actually small, just because its variations are limited by large parameter x in the exponential. So as a result, the way to solve this implicit equation is to expand both terms, left-hand side and right-hand side, in the Taylor series. You can derive it as an exercise for your homework, but for now I will just give you a result. And a result is how to solve this equation for t. And of course, this result can be easily checked by substitution of this t into this implicit formula, and then expanding left-hand side into the power Taylor series in tau, in the positive powers of tau, and checking that left-hand side and right-hand side coincide. But suppose you have this solution as given for now, and then our next step is to change the integration variable according to this equation. And in order to do this, we must take into account both change of the exponential itself and change of the integration measure. And as a result, after substituting this t in both integration measure, which is this term of the integrand, and to the exponential, which is that term of the integrand, we come to the approximate expression. So this approximate sign is connected to the fact that we didn't solve this equation exactly, but instead expanded both sides of this equation in powers of tau. As a result, let us now look closer into this expression. So what is the structure of this expression and why we can actually calculate it exactly? So let us expand, for example, these brackets, and we see that first term has the following shape. It is the integral of some quadratic function of tau and square root of 2 d tau. Of course, the shape of this expression tells you immediately that it can be calculated exactly. Again, it is just simply reduced to the following standard integral. Now the second term is a bit less trivial, but for now you should be well familiar with it as well. And let me write it down explicitly. This integral from the first side is not equivalent to the previous one, but again, as you may have remembered by now, it can be trivially connected to the previous one by simple differentiation over parameter. In this case, this is differentiation over a. So as a result, both terms in this expression for k nu can be evaluated exactly, and this is what we actually achieved by this change of the integration variable. We related our, in principle, very complicated integral just to a sum of Gaussian integrals, which we can calculate very well by now. So as a result, each of the terms in this expression can be calculated explicitly, and we arrived to the first two terms of the asymptotic expansion for k nu.